I didn't know if you wanted to get recorded or not. Okay. Last time I gave you a short introduction to graphs, so what I want to do today is go into a little more detail on them, so you'll be ready to take the quiz next week. And what I'll do is I'll move the start date on the quiz up to today, if that's okay. Everybody want to do that? But I won't change the end date. Is that the question?
No. Yeah.
Okay. All right. So, what is a graph? Well, a graph is a picture of functions, relations, whatever we want to call them. It's also used when you're doing systems design work. Gaming uses graphs. I'm going to show you an example today of where gaming can take advantage of graphs. Okay? So graphing can be a pictorial way of seeing what we've been doing with functions and graphs and relations and so forth. So we said last week that a graph is a set of two sets, which is the definition. So a graph is equal to a set of vertices and edges. And the vertices are the dots, and the edges are the lines connecting the dots. Okay? So let's get into a little more detail on some of the definitions. If we have a graph like this, something like that, these dots then, A, B, C, D, and E, are the vertices, and the lines connecting them are the edges. So this might be edge 1, edge 2, edge 3, edge 4. You can see that kind of notation maybe. Okay? We would say that A and B are adjacent. So their two vertices are adjacent if there's an edge connecting them. Okay? So A and B are adjacent, A and D are adjacent, C and E are adjacent, B and C are adjacent. Does everybody see that? So adjacent means connected by an edge. Notice I didn't say connected by edges, connected by an edge. Remember the parent-child situation where we said the parent cannot be the parent of a child's child? That's a grandparent, right? Right? Same concept, right? Adjacent means they're right in connected once. So B is not adjacent to E. It is adjacent to C, though. Okay? All right. The degree. That's the degree of a vertex is really what it is. And it's the number of edges connected to the vertex. So what would be the degree of A? I heard it. 2, right? Yeah, 2. Everybody see that? Because it has an edge here and an edge here, we would say A has a degree of 2. What about B? B is 2 also, isn't it? What about C?
3.
Yeah. Okay? Yes, sir.
What I'm seeing is that basically, like when you said the degree is the edges, which connect, I just look at like where the corner is and see which side corner, like what's on the other side. That's how I see it. Would you say that's an easier way of like remembering it?
It could be. And let's see in a minute because I've got another, I'm going to add one more complexity to it.
Okay.
But what you're pointing out, let me share with the rest of the class. When you see something your way and it works, use it. Yeah, so that's great. When you're trying to learn, don't ever, well, let's say this differently because I don't want to insult other teachers. But you will have a teacher who tells you the way you have to learn, right? Don't always do that. But don't let them know you're not doing that. But just like you did. Come up with a method that works for you. Because that's what you'll remember years from now. When you get something in your mind. Okay? Okay. So that's the degree of a vertex, and you've got it. Now, yes, sir?
If you've got a vertex that's reflexive, would it have a degree of 2 or 1?
Aha, very good point. If I have a self-loop, right? That's a degree of 2. Now this one now has a degree of 4.
Okay.
Okay? Yeah. So a self-loop would be 2 degrees because it has one going out and one coming in. So that brings up another topic. Because notice when I did this, this is what? A non-directed graph? Remember that from last time? Because there are no arrowheads on the edges, it's non-directed. There's no direction. Okay? If I turn this into a directed graph, now I have a set that when you look at it, you know it's ordered pairs when you look at it as a set because A would come before B. Okay, that would be an ordered pair now if I put it into set notation. So we now have another way of looking at degrees. We have in degrees and out degrees. But now that you've got the concept of degree, maybe it'll make sense to you. In degrees are those edges coming in to the point. In other words, where the arrowhead is. Out degrees are the opposite, the ones going out. So for A, how many in degrees do I have?
None?
0. And how many out degrees do I have? 2. For B, what's the in degree count? 1. And what's the out degree?
1.
And for C, what's the in degree? 2. And the out degree is? 1. For E, the in degree is? 0. And the out degree is?
1.
What about D? Can you see it? What's the in degree? 1, 2, 3 actually. And the out degree is 1. Okay. And notice they add up then to the degree that we said before, the total degrees. Okay. All right. If I were to add another edge going this way between A and B, of course that's going to change my in and out count, isn't it? But we would call these two edges parallel edges because they connect the same 2 vertices. So those are parallel edges. Now I guess we have to change this to 1 and this to out now is 2, isn't it? So if you look at that later, I don't think you're wrong. Okay, so let's see what else we need. Talked about degrees. All right, this is an interesting one. If I take and do like this is A, this is B, so this is C, D, and E, and I go like this, and compare that to the original graph I had here without the arrowheads. do you notice that the edges are all the same as the original? I think so. Let's see. I've got D and C connected. C should be connected to
B.
E,
B.
D, and B, isn't it? Yeah. So I need to do one like that. Yeah, now do you know where I was heading with that? Yes, sir.
B and D weren't connected in the original one.
B and D?
Yeah.
Yeah, they're still connected.
B and D.
But they're
No,
not
they
supposed
weren't
to
in
be.
the original.
Oh, they weren't in the original? You're right. So I think I'm still missing something because there are 1, 2, 3, 4, 5 here. There's 1, 2, 3, 4. Yeah, there's 5. Okay. They're the same graph. So what I was really trying to show you is it doesn't matter what the picture looks like. It's about the vertices and the edges connecting them. Because notice, if I had written this original one, forget the arrowheads again, right? If I had written this original one in terms of a set of connected points, wouldn't I get the same thing if I did that as a set of connected points? Absolutely. So we call these isomorphisms, by the way. I think that's the right spelling. Because they are really two pictures for the same thing. Okay. And of course, in gaming, we talk about morphing, right? Okay. All right. Add degrees, in degrees. Okay, let's do some game theory.
Question.
Yes.
Would it be more difficult to do it on like a 3D model or something like, you know, trying to do like yeah.
You ever played 3D checkers or 3D
Oh, yeah.
chess?
Yeah.
Yeah, exactly. But can you do it? Absolutely. Yes. So, yeah, and are you in gaming? Okay. But you can only imagine what people in gaming are going through, especially with today's tools that we're having, the goggles that show in 3 dimension, right? Is anybody working on that, by the way, in here? In gaming? How many in here are in gaming? Okay. So you're thinking about this stuff, right? Only to get headaches, right?
Yes.
One of the interesting things about gaming, before I get into a game, if you were to go back to, say, 1980s, when the PC first arrived and we first started thinking about really, well, actually before that we had Atari and all those types of gaming machines. And they look very, very crude, don't they? Pong is an incredibly crude game. And you look at it and say, wow, were the people not very smart back then? Do you know what they would have done if they had the tools you have? So you think about it, the tools that you're using to create games were written by the folks that went through the struggle of even thinking about how do you start programming pixels? How do you start connecting pixels and showing actions? How do you show a man or a woman or a figure on a screen? But what do? You pull them out of libraries, right? Or you pull libraries of the way that a person runs. Somebody took a lot of time to program those libraries. So, I don't know whether you know the famous quote from Newton, but everybody knows what Newton did, right? He picked apples. He discovered, or they give him the credit for discovering gravity. What else did he do? Discovered the calculus. Okay. But at any rate, Newton was honored by a lot of the societies back then, but he was a fairly humble man. And one of the famous quotes from Newton was, "If I appear to see further than others, it's because I stand on the shoulders of giants." Always think that way. When you see that you've got incredible tools to work with and can do, you are incredible. You're becoming a giant, right? Somebody's going to stand on your shoulders later. But just give credit to all those people that went before you and say, wow, am I fortunate to have that? Okay? It's always a good way to think. But anyway, enough philosophy for today. Let's look at a game. And this is probably a game that you've seen a version of, but I'm going to show you how to solve it using graphing. Because this is how you want to go through the logic of gaming theory too, game theory. So, you've got a project or a problem where you've got to transport a cabbage, a goat, and a wolf from one side of a stream to another. And you've got a boat that can only handle yourself and one of these items, right? If you leave one side of the stream with the goat and the wolf will eat the goat. If you leave that side with the goat and the cabbage will eat the cabbage, right? So you've got to be very careful how you do this so that you don't lose something while you're gone. So we can lay this out this way. What are our options? Well, we use F to talk about ourselves. I'm not sure why they chose F. But starting out, we've got the cabbage, the goat, and the wolf, and we'll use a straight line to mean the stream. Okay? So there's the starting position. All right. We can also go from there to just taking ourselves across the stream, right? That is an option. Maybe not a good one, but it's an option. So you put down all your options. We could talk about this. I don't know if you can do that, but it's worth looking at. You could look at fox, cabbage, wolf, and goat going across. Okay? So we've got 4 different things that we can do. Now, this is the starting position, so we'll circle this twice and say there's our start place. And we will put then where we can go from that start position in terms of other things we can do. Well, one thing we want to do is we want to say a square means that's terminal, can't go any further. And circles mean options that we could do as far as that one was concerned.
Why is the top one end?
I'm sorry?
Why is the top one end and not the second one?
Why is the top one?
No, the top
No,
one.
because you're still there.
Because if I go across the stream, the goat is going to eat the wolf. Or the wolf's going to eat the goat, I'm sorry. We learned that in a previous section, didn't we? Yeah.
On the second one, didn't you have to take the cabbage across at some point?
Down here, it's impossible to do, isn't it? But it's still safe. Because I'm watching the goat and the wolf. Down here it's safe because the wolf won't eat the cabbage. Okay? So that's just one way of looking at it. But let's take the starting one up here because that's really where we want to start. We said that's the starting point. And what we said is that what we can really do is we could leave all of them and go across the stream ourselves. We could leave the goat and the wolf and take the cabbage across the stream with us. We could leave the cabbage and the wolf and we could go across with the goat. Or we could leave the cabbage and the goat and go across the stream with the wolf. Okay?
Take the goat.
Now, take the goat. This one, we don't want to do we? Because we left the goat and the wolf, and somebody's going to get eaten. This one, we can't do either because, because the goat and the wolf are still there. So we can't do that one. Can we do this one?
Yes.
Yes, because the cabbage and the wolf are okay together. Can we do this one? No, because the goat will eat the cabbage. So that means that this is the only one going forward, isn't it? Well, if we take this one forward, what can we do? Well, I bet the only thing that we can do, because we don't want to just take the goat back, do we? Or we'd be back at our beginning. So all that we can do is leave the goat and go back ourselves. So there's really only one option from that point. From here, though, we have two options. I can take the cabbage across and leave the wolf, can I not? Okay. So if I did that, down here, I would have the wolf, and over here, I'd have the cabbage, the goat, and of course, and that would be okay, wouldn't it? If I instead took the cabbage across, the wolf across, I would have the cabbage and the wolf and the goat and me. And both of those are okay, are they not? Nobody's going to eat anything, are they? While I'm gone? But what must we do here? Well, we must take either the goat or the wolf back, right?
Take the goat.
Yeah, because if I, well, let's see. What if I just went back? I can't leave the wolf and the goat. That's this one. Okay. Yeah, take the wolf back. So,
No,
You go back.
Take
to
the goat.
your starting point.
take the goat back, yeah, right here.
Like you would have to go,
You have
take
to
the
take
goat back, and then take the cabbage over, and then take the goat.
Oh, that's what it's doing. Okay, I got it. Looking at the wrong square here. Yeah, take the goat.
Because if you're going back and forth, you would have to.
Mhm.
Take the goat back. Take that.
Trying to see what the markers here are. Actually, we're in trouble, I think, in both cases. Let's see. If I take the goat back, I'll have cabbage, goat, and man, and on the other side I'll have the wolf, right?
Now you let the cabbage leave the goat.
So now, yes, so now what I can do is I can leave the cabbage and take the goat, right?
Take the cabbage.
I'll take the cabbage, I'm sorry. Leave the goat and take the cabbage. Then we can go one more step this way, can't we? And leave the cabbage with the wolf, go back to the goat, and then down to everything all the way on one side. So that's the way this one then you can string to the same end. Okay. So that's the idea of how you can put together a game in terms of a graph, where the vertices are the conditions and the lines are the actions of where I'm going next, okay? All right. I just wanted to show that to you. Okay. Let's talk about walks and paths. A walk is a connections of vertices using edges to move from one vertex to some other vertex. So if I have a graph A, B, C, D, and I want to go from A to D, well, I can go A, B, D, can't I? That would be a walk. I can go A, C, B, D. That's another walk. Anybody see any other walks? What if I got lost? A, C, B, A, C, B, D.
Wow.
I don't know if I admit it, but you probably had a walk like that at one point or another. Where was I going? Oh, yeah. So, walks are a way to get from one vertex to another, but you may repeat edges along the way. So in this case, where I did A, C, B, A, I then repeated this edge, and then went to D, right? Okay? So it's with repeats, edges, repeated edges. So what do you think a path is? A path is without repeated edges. So, for paths, I'd have A, C, B, D, that would be one path, and I would have A, B, D would be another path. And there are two paths. So we say there are two paths between A and D. How many walks are there from A to D?
Infinite amount.
Infinite amount. Right answer, yes. Because how many times you go around that cycle before you figure out, I'm stuck. Okay? They all count as walks. So when you see this on a test or a quiz, big hint, there are two paths and infinite walks. Okay? Okay. Now we talked about connected last time. If I had E and F over here and a line connecting them, this would be a non-connected graph. Well, pictorially it looks that way, doesn't it? But connected means that I can get from any vertex to any vertex by connections, by paths, right? And because I can't get from anything to E, F from this one, then it's not connected. All right. Okay. So, let's talk about circuits and cycles. Notice that with A, B, and C, I can go around here, I can start with A and I can end with A, can't I? We call that a cycle. Okay. Now, if the whole graph can be done that way, the graph would be a circuit. This graph isn't a circuit, is it? What if I connected C and D?
No. Wait, but we still have EvenOdd.
Now, I can start at any point and follow the graph and get back to that point, can't I? So that's a circuit.
In a circuit, are you allowed to repeat edges?
No. And with a cycle, you don't either. Otherwise,
Is that one a circuit?
this would be its own cycle, wouldn't it? Or before I had this, you could have gone down here and then back up.
Would you
So
not
that's
have,
not a circuit, is it?
would you not have to go between B and C? if
I don't think
started-
you have to repeat I don't think you
Well,
have
yeah.
to go on every edge.
Oh, for a circuit.
Yeah.
So what, so.
Good
I thought-
question. Let's make sure here. Yeah, a circuit is a closed path, yeah. Yeah, just that the initial and terminal vertices are the same.
For
That's
a
all that does
cir-
it.
For a cycle or circuit.
Yeah, for a circuit. Or for both. They're both defined as I can start here and get back to here, right?
Right.
A circuit is the whole graph.
You touch every point in it, and you still end at
So
the
I
same
go from
point?
C to D to B to A and back to C.
Oh, you don't
Yeah,
have to
that's
touch
for
every
the whole
edge
graph.
there.
Yes,
Oh, okay.
yes. Okay? Okay. So, let's talk about Ewer and Hamilton, because they are talking about circles and cycles. There's a puzzle called the Bridges of Comus Berg in Prussia. Prussia was Russia, right? Early Russia. And this town had a river going through it, but it had also two rivers coming together in the center of town. And it had an island in the river. There were bridges that went across to the island and across to the peninsula, joining the two. Now, on Sunday afternoons, of course, they didn't have any television back then, so they had to do something. On Sunday afternoons, the people of the town used to take walks. But somebody came up with a puzzle. Said, can somebody figure out how to start somewhere in here and walk in such a way that you cross every bridge in town and get back where you started, but only cross the bridge once? Do you think it can be done? Yeah?
Yes.
Who said yes?
No.
Where would I start?
The bottom right? Yeah.
Down here?
Yeah.
So I start here. Where would I go? Well, to here, right? Where would I go from here?
Okay, wait. 1 second. I gotta remap it out because I was looking at it when you first said it.
Possible.
No,
Can't
you
be
still go
done.
right there.
I could go right here, right?
Yeah.
And then keep going? Or should you want to go this way?
And you have to come back to the same bridge that you started at, right?
Yeah, you have to end at the same point.
Okay, so you go straight.
Yeah, but you can't cross the bridge more than once.
You go up then.
Okay, so go up this way. So let's
That's all.
walk this
It's
way.
Well, the
impossible.
question is, can you start on the peninsula?
Yeah, you can start on the peninsula.
Then it makes it a whole lot easier.
Okay?
How'd you get to Peninsula?
Let's start on the peninsula.
That's 3 paths to the peninsula.
So if there's 3 paths, dude, if you start on the peninsula, you can't end on it. If
It's
you
an
start on
odd-
the peninsula, you leave the peninsula, you come back to the peninsula, then you leave again. You can't get back. It's impossible.
Impossible.
It's impossible.
It is impossible, isn't it? Yeah. Now, you were right on the right path on the right direction to figure out logically how you figure a puzzle like this, right? It has to do with even and odd edges coming into a vertex. Well, how would we actually show this? Isn't this actually a vertex up here, and another vertex here, and another one here, and another one here? Okay. And if I were to show these as vertices, then I might want to draw it like this. I think that's it. So I've got, joining this one and this one, I have 2 edges, don't I? And joining this one and the bottom one, I have 2 edges. And then joining this one and this one, I have 2, and then I have 1 down the middle. Okay. So, what's the degree of this vertex? 3, right? 3 edges. What's the degree of this one? 3. The degree of this one?
3.
And what's the degree of this one?
5.
Okay? They're all odd, aren't they? And what'd you say about odd degree?
No matter where you start, you can't end up getting back there.
That's right.
And being done.
If I had a vertex like this with 2 edges coming in, I could leave on one and come back on another, could I not? Oh. So what's the secret to something like this?
Swim.
You need you need some even vertices in here, don't you? Okay? And in fact, you need at least 2. And why did I say at least 2? If you had 3, you could go through that, couldn't you? Okay. If I were to add like that, I'm taking a little risk here, but I think I can do it. That one should be doable.
Are those points more vertices? Or?
Yeah, those are 2 more vertices.
Ah.
The degree of this vertex is what? 2. And this one has a degree of 2. Okay. Now, if I were to start here, I could go to here, to here, to here. I could go back again, go to here, go to here, to here, back to there, and then here, couldn't I?
You miss one.
You missed the number 3 to number 5. The peninsula to the
I
island.
missed this one?
Yeah.
Okay. So we start here, we go here, 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 here. Now I'm back again. So I go here.
And then you're stuck.
Yeah, then I'm stuck. I don't want to do that. So I go here. Let's see. Yeah, probably don't want to do it in that direction. However, without doing it that way. The answer to it is that if you have even degrees, you can start and end there, okay? But for, oh, I know what it is. No, I'm sorry. For an odd degree, you must either start or end there, don't you? Because for an odd degree, what's going to happen? Let's take these out. It's the fact you cannot have that many odd degrees. If I take this and I go out and I come back, then I can go one more place and I'm finished with that one, aren't I? So that could be a starting point. If I have a second one, it could be an ending point. But if you have an even degree, you're more likely to go in and out of it again. So let's take that a little bit further. So a Euler circuit, first of all, which is what this is called. Everybody knows who Euler was? Euler was a great philosopher and a mathematician. So a Euler circuit is a circuit that contains every edge and every vertex and each edge only once. Okay, so that was the problem. The Euler circuit would be one where it would work. Now this one would work, wouldn't it? If I take that one bridge out, notice this is now 4, this is 2, this one down here is 1, 2, 3. So this vertex for this side of the river is 3, and this one over here is 1, 2, 3, isn't it? So if I start here, I can go down here and up here and then down here, can't I? So what have I done?
That's a circuit, not a cycle, right?
That's correct. A cycle is a simple circuit, is what it's called. Okay. All right, so the idea is that you must have 2 odds, but only 2. Can't have more than 2. Okay.
But you said that was a, sorry, but you said that was a circuit or a cycle?
Circuit?
Circuit.
It's a Euler circuit.
Where does it start? Oh, it's a Euler circuit. So a Euler circuit doesn't have to start and end at the same point?
No, no.
But a regular
It just
circuit
has to
does.
cover every vertex and every edge.
Okay, but a regular circuit does? Or no?
No, same thing. It just,
Oh, just has to touch
Yeah.
every point?
yeah, yeah. Okay, so that's a Euler circle. Okay, I think that's as far as I want to go. There's also a Hamiltonian cycle, but it doesn't really add much to the discussion, okay? So, I will move the quiz up to open today, but still closed next Sunday. So on Monday, try to get the quiz done once, because remember, next week we only meet on Monday. Wednesday and Friday, I'll be in conference. So that should get us still on schedule where we should. Okay? All right, have a good weekend.